years old, I was involved in a traffic accident, a head-on collision, quite literally. Car versus bicycle. I was on the bicycle. I survived, but I suffered head trauma and a broken collarbone. And all of what I'm telling you is secondhand information because I don't remember anything that happened on that day. 20 years later, I'm a neuroscientist, and I work on the biology of learning and memory. My own personal experience of memory loss has absolutely nothing to do with why I study memory now, but it serves to illustrate a particular paradox of memory, which I have always found confusing. How is it that we can remember a single experience for our lifetime, and yet at the same time forget things that are centrally important to us? We can recognize a face we have not seen in years or a song we have not heard in decades, but aging and misfortune results in us losing memories, not only trivial, but the ones that matter most. Why is it that my brain has no ability to remember what happened on that day, but my collarbone will never forget? Changes that happen to us biologically generally don't go back. We cannot forget our scar tissue. Our tattoos don't disappear. Our hair turns gray and stays that way. But our long-term memories, which have the capacity to last as long as we do, can also be obscured. This is Thomas Dixon. He suffered very severe head trauma, and now he can't always remember what he did on any given day, much like the amnesic protagonist in the film Memento. But Dixon doesn't use tattoos to combat his memory loss. Instead, he has developed the far more sustainable solution of outsourcing his everyday memory to a custom-built memory smartphone application. Dixon's case serves to remind us how devastating amnesia, beyond simple forgetting, can be to our functioning as individuals. Our memories are central when we physically navigate the world, when we participate in social situations, and when we educate our children. Without memory, we can't make meaningful predictions about the world, and we can't learn about cause and effect. It's no exaggeration to say that memory is also key to our success as a species. As humans, we can use language to communicate some of our memories, our culture, across generations, at a much faster rate than biological evolution can allow. But memory is not just about us interacting with the world. Each of us as individuals is the sum total of all the experiences we have accumulated in our lifetimes. You are your own unique story, with some internal life lived on your memories. And when amnesia hits due to trauma or illness, you lose a part of yourself. But what is amnesia? Broadly defined, amnesia is a deficit of memory function due to some specific stereotyped cause: head trauma, stress, drug and alcohol abuse, nutritional deficiency, oxygen deprivation, epilepsy, brain inflammation, infectious diseases, aging, and neurodegenerative disorders ranging from Alzheimer's disease to multiple sclerosis. Like cancer, amnesia is a symptom of many different brain problems, and so it's a case where treating the symptom may have more wide-ranging utility than treating any one particular cause. Some of us have already experienced amnesia to varying extents due to one of these causes. Even if we haven't, many of us will. In the developed world, 1 in 3 of us who live to be over 65 will develop some form of dementia, and as long as our standard of living remains high, the memory problems of the elderly will become the most costly and prevalent public health problem that we face. In our younger years, most of us tend not to think of ourselves as amnesic. But how many of us remember our first storybook or our second birthday party? How many of us remember taking that first step? 33% of us will suffer dementia, but 100% of us have experienced infantile amnesia, the global developmental loss of memories formed in the first few years of childhood. Many of us experience infantile amnesia numerous times, at least vicariously. Our children will simply never remember or appreciate the time and energy we put into them in their early years. Memory loss, whether from aging, misadventure, disease, or growing up, is fundamental to our experiences as humans. It's just a fact of life. My question is, what if we could get those memories back? What if those memories were not truly lost, but just locked in our brain and not really accessible? Now, we often think of memory as something like a book, and we're told that in amnesia, the book has been burned, or the pages have been torn out, or the lines erased. But what if the book was still intact in the library and we just forgot where we left it? Getting to the answer of this question is crucial, because in cases of memory access deficits, the memory is still in the brain and we just need to find it. As a neuroscientist, my research revolves around one central question: how are individual memories stored in the brain? In order to answer this question, we need to be clear about what memory means. We need to define it. But defining memory is a little bit harder than you might think, precisely because it's so tied in with our subjective experiences of the world and our personal identities. But we can broadly define memory as knowledge that is accumulated in your lifetime by a process of learning and distinct from your genetically encoded instincts. Learning must involve a material change in your brain. And the particular material change that accounts for a specific memory we refer to as a memory engram. Now, up until recently, we studied memory in the brain by looking at the effect of brain damage and disease on memory function, in essence by studying amnesia. We looked for someone who was suffering from amnesia, and we went to see what was going wrong with their brain. And we concluded that whatever brain region was damaged or malfunctioning was probably important for the storage or maintenance of our memory engrams in general. As a result of this approach, we know quite a lot about the various causes of amnesia, but perhaps not quite so much about memory itself. To make progress, we need to differentiate between the act of remembering from memory information content. We know from daily life that remembering is a highly volatile activity. Sometimes you get it right, sometimes you don't. Just because you forget something today doesn't mean it won't return to you tomorrow. And the circumstances in which we recall a memory affect how we view it. Remembering is an activity. It's influenced by context, mood, alertness, sights, sounds, and smells, alcohol, caffeine, or a crowd of people looking at you. Unlike remembering, memory itself is not an activity. It's not something that we do, like learning or remembering. Memory, the biologically encoded information, is the long-lasting and stable change that is caused by learning. It can lie dormant for our entire lives, being called upon only when necessary or perhaps just randomly by the taste of a cookie. And just as we can lose access to stored data in our computer hard drives, say if the power is cut or the screen is broken, we must be open to the possibility that our brains may lose access to our memory engrams due to neurological causes which affect our ability to remember, but without damaging the memory engrams themselves. So if we are to look for memories in the brain, how can we expect to identify them amongst billions of brain cells connected by trillions of different synaptic connections? Well, we can step out of science for a moment and take some inspiration from literature. In Arthur Conan Doyle's A Scandal in Bohemia, Sherlock Holmes is tasked by the King of Bohemia to retrieve a compromising photograph from the home of Irene Adler. Dr. Watson asks how Holmes will know where in the house to look for the photograph. And Holmes retorts, "I will not look. I will get her to show me." By releasing smoke into the house, Holmes identifies the photograph's location based on his subject's behavior, because, according to Holmes, when a woman thinks her home is on fire, her instinct is to rush to the thing which she values most, at least in the 19th century. If we are to identify a particular memory engram in the brain, we can take a similar approach by smoking out the location of the brain, of the memory, by hijacking the normal biological processes of memory allocation and having the brain show us where the memory is. Now, it happens that the brain allocates information partly by inducing specific genes to produce specific proteins. We can take advantage of this approach. By copying these activity-induced genes, we can make artificial versions to express fluorescent proteins in cells that were specifically activated by a given learning episode. In other words, we can make specific brain cells light up when they encode a given memory, the memory engram cells. How do we know these cells contribute to a specific memory? What would we require for it to say that something carries specific information? Well, activating them should result in targeted memory recall. Over the past 5 years, through experimental studies beginning in the Tanagawa lab at MIT, I and others have shown that if we label cells that are activated during learning and stimulate them thereafter in awake-behaving rodents, we get targeted recall of specific memories. We can now label and manipulate particular memory engrams in rodent models. Now, mice are pretty smart. They have to have survived in the world for so long when surrounded by predators. And we can train them to do different behavioral tasks, such as learn that a particular room is good or bad, learn complex associations, and also navigate mazes. Using a behavioral paradigm, I train mice to do a particular task, and then I induced amnesia by drug treatment. And the mice appeared not to remember that particular task. They were amnesic. But then, when I stimulated the engram cells for that memory directly, the mice showed perfectly normal memory recall. The functional engram was still present in the brain. This was also the case in mice that we genetically engineered to develop Alzheimer's disease. The amnesia was a deficit of memory recall, but a functional engram remained inside the brain. And I think the same is true of many other kinds of amnesia. This points to some very exciting prospects. It means that in many cases of amnesia, the physical data of memory persists beyond the functional experience of amnesia. Amnesia can therefore be factually attributed for the first time to a deficit in memory access, but the information itself survives. We now have solid ground to begin to develop non-invasive interventions, such as drug treatments and cognitive behavioral therapies, to help reconnect human amnesia sufferers with some of their memories. So now the challenge for us in neuroscience is to identify which brain regions are doing the remembering and what is the physical basis of memory content itself. In neuroscience, we're taught that to understand memory, we need to think of it as a particular physical change in the brain or some vital molecular change. This is the wrong approach. Understanding memory is not just about understanding the ink that it is written in. It is also about understanding the language and meaning of the words that are written. If you walk into the neuroscience building at MIT and you look up, this is what you'll see. 100 gold-plated neurons suspended from the ceiling. A wonderful sculpture by Ralph Helmick. But if you climb the stairs and look down at the same sculpture from a certain angle, this is what you'll see. Where is the memory for the image of that brain? Is it in the shape of the brain cells? Is it inside the brain cells? Is it in the gold? No. It's not an arbitrary physical substance. And neither is it mystical or vitalistic. It is information. Information encoded in the specific constellation of brain cells. When we label memory engrams in the mouse, we see changes in the permanent anatomical connectivity between brain cells. And this feature of the engram survives amnesia. It remains intact even though the mice appear not to remember, and stimulating these neuronal constellations results in us getting the memory out. Changes in the hardwired connectivity of the three-dimensional architecture of the brain provides a long-term and stable way for plausibly storing a long-term memory. If you want to store a memory for your entire life, you don't write it in the sand. You engrave it in stone, in a stable state. The fact that memory is information is the reason that we can outsource it so easily to places outside of our brains, to smartphone apps, to computer hard drives, to books, to cave paintings, and in the future, to artificial intelligence. We can't yet manage to outsource our skin or our liver function. These are purely mechanistic parts of our bodies. But since the earliest days of human culture, we have been outsourcing some of the content of our memories. Crucially, the engram state must have meaning for the organism, or else it's not information. That image of the brain only exists from a certain point of view. And similarly, a neuronal constellation must carry meaning from the point of view of a host organism struggling to survive and reproduce in its environment. In other words, we need to learn how to go from a compact and clear but unrecognizable to many piece of information to what it really means for all of us. The idea that memory is formed by permanent engravings in paper or stone or in the brain does not mean that it's immutable, that it can't change. Words engraved in stone can still change their meaning by adding new information. For example, if we engrave one sentence in stone that we may not be particularly happy with, we can evolve that sentence by adding some punctuation and maybe some new words. All of the previous information remains intact, but because of new information, the meaning has transformed entirely. And by this process, we can hope to do something about post-traumatic stress disorder by mutating traumatic memories into more livable ones. This is also how our brains can be tricked by incident, misinformation, and coercion into forming false memories and false beliefs, often resulting in maladaptive behavior. And if you've ever wondered why new grandparents often have a somewhat incomplete picture of what it takes to manage a newborn baby, it's not because you came out of the womb as an 8-year-old. It's because they've taken their own memory engrams of you as a baby and changed them to engrams of you as an infant, eventually to more traumatic engrams of you as an adolescent, and, if you're lucky, to mature engrams of you as an adult. But the point is, memory evolves. Even though it's stably encoded and not easy to lose, it can still change its meaning. Understanding memory as permanent changes in the brain may even tell us something about our own evolution. Learning in the lifetime necessarily builds on our genetically encoded instincts, and we never forget our instincts. They are part of the permanent wiring of our brains. But where do those instincts come from in the first place? Over time, a particular behavioral tendency becomes so valuable that the whole population seems to learn it. Smiling, sniffing, grooming, swinging in trees, or fear of snakes. But any individual who is lucky enough to develop a genetically hardwired version of that brain circuit, of that constellation, will have an advantage over those who must work in their lifetime to form that brain circuit for themselves. The psychology of a species can thus be intrinsically changed by genetically rewiring its innate microcircuitry in a way that mimics, that copies, an ancestral but learned memory engram. Taking an evolutionary approach within our own lifetime is how we can overcome the paradox of our original question. Why is memory at once so long-lasting and at the same time so vulnerable? The answer is that sometimes a great strength is a great weakness. The great strength of memory is its inherent adaptability. Our memory engrams, like our genes, our DNA, and like our politics, must remain generally conservative and stable. Our survival depends on it. But they must also be able to change. We can't adapt to new circumstances, to new environments. Our memory engrams are central to our survival, so they're not easy to lose. But they can be altered, they can be misinformed, and they can be obscured in amnesia. In nature, nothing comes for free. Every advantage is a potential disadvantage. The risk of losing our own memories in amnesia is part of the price we pay for our enormous cognitive flexibility and the huge cultural and informational potential of our future evolution. But today, understanding memories as permanent changes that last all the way to endgame provides a novel and optimistic framework for developing therapeutics, prosthetics, and external aids for helping to combat memory loss in the old, the young, and the misfortunate. Medical interventions can heal lacerations, broken bones, and damaged limbs in things that won't heal on their own. What if we could reconnect the brain with its apparently lost memories and forget about amnesia? Thank you.